Welcome everybody, I'm about to get to the video. I just want to let you know this video is part of my kernel development video course. So if you like this video, you can get the full course in the video description. Now to the video. Hello and welcome back everyone. I'm going to explain to you about the PS2 mouse in this lesson, ready for implementing it. So the PS2 mouse and the PS2 keyboard, as you can see from that image, they share the same controller, okay, which means that they share the same ports that we read and write to, okay. That's an important distinction. So how do you know that if it's a mouse or a keyboard action? Well, because the interrupt numbers are different. So the keyboard interrupt, when that's invoked, you know you're dealing with a keyboard stroke, some sort of keystroke or something. When there's a mouse click, a mouse interrupt will be invoked, and you know you're dealing with a mouse action. That's how you know. And but they share the same data lines, so that's important to know. So obviously you have the command port and the data port. So if we were to read from the command port, and the first bit 1, is set, then that means the controller is currently processing something. So we shouldn't send any commands to the command port, okay? When it's 0, we're ready to send new commands to it. Likewise, on the output buffer, if the status bit 0 is 1, then that means the CPU needs to read before new data can arrive, okay? And yeah, you know, just another thing, you can see the ports there that we're using, okay? So the command port's there, 0x64, port 0x64, we can read from there right to there. So we can write commands like enable the second port of the controller, for example, or read the configuration byte. 0x60, that's the data port. So that's where we're reading the actual mouse packets, keyboard packets, or we're writing some commands to it, and so on. And these bits that I just described are in relation to those ports, okay? The data you read from those ports. Let me show you how it works in our system. So first we register our mouse interrupt, and that will be the PS2 mouse handle interrupt function that will be called. But we also enable the IRQ for the PS2 mouse, okay, on the PIC. Okay, that's important. And in the right hand corner, the top here, you can also see the actual port numbers and the mouse interrupt numbers relative to the slave PIC and so on. The next step to get the mouse working, we have to actually enable the PS2 port, which is the mouse. So how do we do that? Well, first we call mouse wait to wait for the PS2 input to be clear, and then we write to the PS2 status port to enable the second port, okay? So where does this differ? Well, we've enabled the mouse interrupts, so the mouse is able to send interrupts, but we haven't enabled it on the controller. So although we've enabled it on the bus that we'll be able to receive interrupts, the controller still isn't listening, okay? So we need to send a second command to the PIC control to the actual PS2 controller to enable that actual second port, okay? That's what we need to do. And when both of those are enabled, then the mouse packets can be received and the interrupts can be invoked, okay? So here's an example of our PS2 wait function. So very simply, we're just reading from the PS2 status port for the actual second bit to go low. Because if you remember at the start of the presentation, I said that by here, status port bit 1, if it's 1, it means the input buffer is full. So what we're doing here, this mouse wait function will wait until it's not full anymore, and then we will be able to continue, okay? And obviously you can put in a type, what type of wait you want to do. So in this particular case, it would be a wait for input to clear, okay? So this is an important function of ours, which will allow us to wait until the mouse is ready, okay? So the next step, guys, after we have enabled the status port, is to read the configuration byte. Now, how do we do that? Well, we send the command to the status port, reconfig byte, and then we wait for the output to be set, okay? Once the output is set, we read the configuration value. So you can see how this works, right? We send a command to the controller, and we wait till the output is ready. When the output's ready, we can read from the output, okay? That's what we're doing, guys. We block, essentially. So once we've read our configuration value, we clear bit 5 to enable the clock, and we set bit 1 to enable interrupts. And this will allow the mouse to fully function, okay? And then we wait for the input to clear again, since the controller may have responded to us. And then we need to write the configuration byte back. Okay, so we've changed the bits, we need to write it back now. And then again, we wait just in case the controller responded to us. So we basically write the PS2 update config byte command. The controller is in the update configuration byte state. We wait until we're acknowledged by the controller by waiting for the input to clear again. And then we write to the communication port the new configuration value, guys. And then the PS2 controller will be in a enabled clock and enabled interrupt state. Okay, so the next step is to call the PS2 mouse write function, which will reset the mouse, okay? And then we need to wait, again, for the output to be set, waiting for acknowledgement. And if we have an acknowledgement, then we know the mouse is plugged in and working, okay? And then we need to wait for a self-test to be completed correctly, okay? This is how you enable the mouse. And then the device ID will be set. And if it's null, then it's an invalid device, so maybe the mouse isn't plugged in. If it's not null, guys, then it determines if the mouse has 3 buttons or not, or if it has 2 buttons. So once we've done all of that, we then need to write to the mouse to enable the packet streaming, okay? And then again, we need to wait for the output to be set, read from the communication port, and check that there's an acknowledgement, okay? This is where we set up the mouse structures in our C program, and we set the device ID. The packet size is 3 by default, but if it has a scroll wheel, i.e. 3 buttons, that's what I meant when I said 3 buttons, then the mouse packet size will be 4 bytes, okay? That's why we need to check that device ID. And one more thing before we go to the video, this is what the mouse write function looks like, guys, okay? So we wait for the output to be set, we set the status port to write to mouse, we wait, and then we send the byte over the communication port, okay? That's how the mouse write works. Okay, so now let's get on with that video. The mouse packets determine if there was a click or a mouse movement, okay? So the standard PS2 mouse packet is 3 bytes, and this is how it's set up. So bit 0 of byte 1 means the left button was pressed. Bit 1, the right button was pressed. Bit 2, the middle button. Bit 4 is the X sign. Bit 5 is the Y sign. Bit 6 is the X overflow. Bit 7 is the Y overflow. You do not need to worry about any of those. Okay, only the left button and the right button, middle button bits. That's all you need to worry about, because the X movement is in byte 2 and the Y movement is in byte 3. That's why you don't need to worry about those overflow bits and so on. Okay guys, so I created a little simulation to show you how these mouse packets will be received by the kernel. So first let's scroll down so you can see the very first byte. Bit 0 determines if the left button is clicked. Okay, so if that's 1, the left button was clicked, okay? Bit 1 determines if the right button was clicked. Bit 2, middle button. Bit 3 will always be 1 forever, okay? And these ones you don't need to worry about, these bits here. The second byte will be the X movement of the mouse. The third byte, the Y movement of the mouse. Now, you might be thinking it's going to set the X to something like whatever X position the mouse should be on the screen. But that's not true, because there's a very small resolution. It's only a byte, remember. So what happens is when we move to the left, you can see we get some negative numbers there on the right with the X delta. That means we're going left. When we move to the right, we're getting positive numbers. That means we're going to the right. Okay? And you can see we only have resolution within a byte range. Okay? And I think it's a signed char actually. So maximum 0 to 128. Okay? Of resolution. So what we instead do is we say if the X delta is below 0, then we know we're going left. So we'll adjust our little mouse graphic on the screen to go however many negative pixels, like this is -1 right now, for example. So we'd set the position -1 pixel to the left of the mouse on the screen. And again, if we go to the right, we can see we get a X2 there. So we will move 2 pixels to the right. Okay, and this is how the 3-byte mouse packet is working. You can see when we left click, we can see the status byte is changing, which contains those bits that determine if we left click. So that's how that works. When we right click, there's other changes. When we move too quickly to the left, we can see we get a status byte at 24 because these other bits are changing. So yeah, guys, this is how the actual mouse packet works, okay? So you can't expect the mouse to give you the exact screen position it should be at. There's just not enough resolution, okay? So we just need to basically take these values and use our initiative. So if it's negative, that the mouse is moving to the left. If it's positive, the mouse is moving to the right. And then we take these relative values and we add it to our current mouse position, our mouse graphic position. And then it will make our graphic go left or right based on how you move the mouse. Same applies for up and down. You can see if I go up, we get a negative Y delta. If I go down, we get a positive Y delta. So that's how the 3-byte packet works for the mouse, guys. It's very simple. So we're going to be implementing that mouse very soon, okay? So thanks for watching this lesson.